In this video, we're going to look at energy level diagrams and electron configurations. When completing an energy level diagram for an element, the lower energy orbitals must be filled first. Remember that each of the orbitals, or the circles in this diagram, can hold 2 electrons, one with a positive spin and one with a negative spin. So the procedure is to count the number of electrons in an atom, which is equal to the number of protons. You fill the low energy space with an electron, and then before moving to the next energy sublevel, you add an additional electron of opposite spin. If you have multiple orbitals in the same energy level, spread the electrons out as much as possible before doubling up, and then you write the basic electron configuration below. So let's take a look at this energy level diagram that we have here. So these are all the possible orbitals that an atom can have. But remember, they'll only get filled based on the number of electrons available to that atom. So based on the number of protons that atom has. So in the first energy level, so this is when n is equal to 1, right here. When n is equal to 1, remember that we only have one subshell, and that's the S subshell. The S subshell only has one orientation in 3D space, and therefore it only has one orbital. That orbital can fit 2 electrons, and so therefore the first energy level can only fit 2 electrons. When we go up to n is equal to 2, remember we can have the S subshell and the P subshell. Note that there are 3 orbitals for the P subshell because the P subshell can have 3 orientations in space. It can have antinodes on the x-axis, antinodes on the y-axis, and antinodes on the z-axis. So there's 3 orbitals here. Each of them can fit 2 electrons, plus the s orbital with another 2 electrons, so a total of 8 electrons. In the third energy level, we have S, P, and D right here. This is the third energy level. And remember that D has 5 possible orientations in 3D space, so therefore 5 orbitals, each of these circles containing 2 electrons. What you'll notice here, though, is that 3D is at slightly higher energy than 4s. So even though 4s is at a greater distance from the nucleus, the S subshell has much lower energy than the D subshell. So the combination of 4s is still lower than 3D. So you have to fill 4s before you fill 3D, and then you fill 4p. So I think the best way to go about this is to use examples, and let's look at the procedure right here. Okay, so the first example that we're going to take a look at is oxygen. And so we're going to count the total number of electrons. Well, to find the total number of electrons for oxygen, we're going to have to take a look at our periodic table and find the number of protons for oxygen. Okay, so here's my periodic table. I see that oxygen has an atomic number of 8, so that means it has 8 protons. So if it has 8 protons, that means oxygen has 8 electrons. So what I'm going to do is I'm going to start from the lowest possible energy first. That's my 1s orbital. So I start over here and I write 1s, and instead of a circle, I'm just going to draw a little line here to indicate the first or the 1s orbital. All right, so I'm going to fill this with electrons, one with an up spin and one with a down spin, or clockwise spin and counterclockwise spin. Okay, so that's only 2 electrons. I have 6 more electrons to place. So after the 1s, I've got a big jump from 1s to 2s because the distance from the first energy level to the second energy level is the greatest. So I make a big jump here and I go 2s, and then I have another orbital right there, the 2s orbital. Again, I fill that with 1 electron of upspin and 1 electron of downspin. Right, still have 4 more electrons left to place, so I go to the next subshell, that's my 2p, and I draw that out. And when I draw that out, I make sure that I indent the 2 p orbitals. Remember, there's 3 of them, 3 orientations in 3D space, one along the x, one along the y, and one along the z. Now, because I have 4 electrons to place, as we see in the procedure, if I have multiple orbitals in the same energy level, spread the electrons out as much as possible before doubling up. So this rule right here is known as Hund's rule. Electrons must be spread out within a subshell with the same spin before doubling up in orbitals. Okay, so I place 1, 2, 3, all with the clockwise or up spin. And now I still have 1 electron left to place, so now I begin doubling up. And I double up right here, and there I have my 8 total electrons. So that's my energy level diagram for oxygen. And the last thing I have to do is I write the electron configuration. So for that, I'm going to say oxygen with a atomic number of 8 is given as 1s, and there's 2 electrons in that energy level, or in that subshell. Then 2s, 2 electrons, so I write 2, and then 2p, and there are 1, 2, 3, 4 electrons. I can make sure that this is right because the total number of electrons should match the number of protons. The next element I'm going to look at is magnesium. So again, I'm going to pull up my periodic table. I'm going to look at the number of protons in magnesium atoms, and that's going to be the number of electrons I have to place. So let's pull up our periodic table. Okay, I see that magnesium has 12 protons, so that means I have 12 electrons to place for magnesium. Again, I'm going to start from the lowest energy level, so the 1s, before moving up. This is known as the Aufbau principle. So I see it right here, Aufbau principle. Electrons must be added to the atom starting with the lowest available energy level and subshell. Okay, so I've got 12 electrons to place, so I start with my 1s, all right, and I place 2 electrons. I jump up to the 2s, again, big distance there, and I place 2 electrons. Then I go to 2p, there's 3 subshells there, or there's 3 orbitals within that subshell. And I start filling this out, and recall that I have to fill them out with the same spin before I double up. Okay, let's count the total number of electrons I have here. 2, 4, 6, 8, 10. I need to have 12 electrons, so that means I need to go up to the next energy level, and as we can see, the next energy level is 3s. Put that there, and I fill that with 2 electrons, so I now have 2, 4, 6, 8, 10, 12 electrons, and I've completed the energy level diagram for magnesium. So now I'll write the electron configuration. So I've got a atomic number of 12 for magnesium, 1s2, 2s2, 2p6, 3s2, and that's my electron configuration for magnesium. All right, before we continue and do bromine, try to pause the video and see if you can do this one for yourself. You're going to need lots of space, so definitely write smaller than you would normally for the first two, because we're going to have to go to a very high number of energy level and subshells. So I'm going to pause the video, and when I come back, the answer will be given. You can check your answer accordingly. Okay, so as you can see, I've started doing the energy level diagram for bromine, but I'm not quite there yet because I need to place 35 electrons, and what I have right now is 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm not quite there. But what I have done is I've completed the 3p subshell, and I have to remember that after 3p, I must now fill 4s before going to 3d, because 4s is lower energy than 3d. And so that's in accordance with the Aufbau principle. I must go from lower energy level to higher energy level. So after 3p, I'm going to go to 4s, and I fill that with 2 electrons. After I've filled 4s with 2 electrons, then I go to 3d, and as you can see, 3d is further indented. So I go 3d, and I put them over here to the side, 1, 2, 3, 4, 5. Okay, fill those up. All right, and then I can go to 4p. And now that I'm in my last subshell here, I have to look, and I've got 35 electrons to place. So let's count how many electrons we have here. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, which means I have 5 electrons to place. Well, according to Hund's rule, they must be spread out within the subshell with the same spin before doubling up. So I'm going to write them as follows: 1, 2, 3, 4, and 5. And there is my energy level diagram for bromine. And so I finished this off by writing the electron configuration. So bromine with an atomic number of 35, 1s2, 2s2, 2p6, 3s2, 3p6, and then I go to 4s2, then 3d10, and then 4p5. And that's my electron configuration for bromine. So typically, I find that students can manage to do this pretty well on their own. But if you need like a memory aid, this can help if you want to draw this out for yourself. You do 1s, 2s, 3s, 4s, 5s, 6s, then the p's, then the d's, and the f's, and then you draw arrows to show the order in which you fill the subshells. Okay, let's move on. We're now going to do energy level diagrams for anions, and these are the same as the diagrams for atoms, except that because they're anions, they're negatively charged, so they've gained electrons. So you add extra electrons to the total number of electrons, and then we distribute them. So the sulfide ion is the negatively charged sulfur ion. And so if I take a look at my periodic table, we can see how many electrons sulfur has gained. So if I look at my periodic table here, sulfur has an atomic number of 16. So sulfur atoms have 16 electrons. But recall that if they become ions, sulfur is a nonmetal. Nonmetals have a tendency to gain electrons, and they want to gain sufficient electrons to have an electronic configuration similar to a noble gas. So sulfur will gain 2 electrons so that it has the same electron configuration as argon, or we say that this is isoelectronic with argon. So sulfur is going to gain 2 electrons for a total of 18 electrons. So now it's just a matter of doing my energy level diagram for sulfur with the 2 extra electrons. Okay, so we'll go 1s. I have my 2 there, 2s, 2 there, 2p, 3s, and then 3p. And so normally here, sulfur would have so this is what sulfur would normally have. But recall, because that's 16 electrons, let's check 2, 4, 6, 8, 10, 12, 14, and 16. But recall that it has gained 2 electrons in its outer shell. So then I'm going to draw another electron here and another electron here. And I'm actually just going to indicate with an arrow that these were the gained 2 electrons. And now that it's gained 2 electrons, it is isoelectronic with argon. So that means it has the same number of electrons, or it has the same electron configuration as argon. Try now doing this with the phosphide ion. So if you look at phosphorus, phosphorus has a the number of protons, or an atomic number of 15, so therefore 15 electrons. And then if we look at phosphorus's position on the periodic table, you can see how many electrons it's going to gain to obtain a noble gas electron configuration. So let's actually take a look at the periodic table and see how many electrons phosphorus is going to gain in order to have an electron configuration similar to a noble gas. Okay, so phosphorus is right here. It's a nonmetal, so it has a tendency to gain electrons. So it's going to gain 1, 2, 3 electrons. So phosphorus will gain 3 electrons to have a total of 18 electrons. And so what you might notice is, take a look, this is going to have the same number of electrons, and so therefore its energy level diagram is going to be the exact same as the sulfide ion. So as opposed to redoing this exact same electron configuration, we'll just write it has the same energy level diagram as sulfide, except instead of having 2 gained electrons, it's going to have 3 gained electrons. And so again, it is going to be isoelectronic with the noble gas argon. Isoelectronic meaning it has the same electron configuration. So that is how we do energy level diagrams for anions. We look at the gained electrons and then we add them. Energy level diagrams for cations are slightly different. We fill the orbitals as we would for a neutral atom, and then we remove the electrons according to the charge from the orbital with the highest principal quantum number. And this procedure seems to produce the correct arrangement as seen in experimental evidence. Okay, so let's take a look at zinc right here. So zinc is right here. So what I'm going to do is I'm just going to do an energy level diagram for the neutral atom of zinc. So if I look at zinc, zinc has an atomic number of 30. That means I've got 30 electrons to place. And I'm going to go ahead and start doing the energy level diagram for zinc. Okay, so to do that, I start over here at the 1s, and I fill that with 2, big jump, 2s, 2 there, 2p, fill that up, 3s, then I go 3p, and 4s, and then 3d. Remember, we fill 4s before we fill 3d because 4s has slightly lower energy. And so when I fill up 3d, I fill it up entirely because that is 30 electrons, and that's for my neutral atom. But I'm not dealing with a neutral atom here, I'm dealing with the zinc ion. And the zinc ion is typically a zinc 2 positive ion, and we can see that on our periodic tables. So that means I'm going to subtract 2 electrons, and I subtract them from the highest principal quantum number, or highest n. So I look at here and I see between 3 and 4, 4 is my highest principal quantum number. These electrons are the furthest away from the nucleus. So these are the electrons that get removed. So what I'm going to do is I'm going to then erase these right here and then circle to show that I have removed 2 electrons. We'll now look at gallium, and we'll find gallium on our periodic table, look at the number of electrons we have for the neutral atom, and then subtract 3 electrons. Okay, gallium is located right here. It has 31 protons, so therefore 31 electrons. If it's neutral, I'm going to remove 3 electrons. All right, so I'll first start off with the neutral configuration, or the neutral energy level diagram, and then I'm going to subtract 3 electrons. Okay, so this is gallium's neutral energy level diagram, and I'm subtracting 3 electrons from the highest principal quantum number, because the highest principal quantum number is the furthest away from the nucleus. And so therefore I'm going to subtract an electron from here, 1 electron from 4p, and then 2 electrons from 4s. So I'm going to indicate that right here, that I took 1 from here. Okay. And I will say removed 3 electrons. Electron configurations can also be used to identify elements. So for example, if I'm given this electron configuration, I need to figure out what the element is. And so element, if I'm saying element, that means it's neutrally charged. And so what I can do here is I can count up the electrons. So count up number of electrons, and that should be equal to the number of protons if it's neutrally charged, which elements are. And then that will tell me the identity of the element. So I go 2, 4, plus 6 is 10, plus 18, 2, 20, 35. I've got 35 electrons here. So if I look on my periodic table, I find which element has 35 protons. Bringing up my periodic table, 35 protons, that's bromine. So this element is bromine. Try this out on your own, count up the total number of electrons, that's the number of protons, and see if you can figure out which element this is. Okay, with 43 total electrons, this should be technetium, so Tc. Okay, so sometimes writing out all these electron configurations can be a pretty onerous task. So what we'll do is we'll look at the electron configurations for these elements and see if there is a shorthand or a faster way that we can write these. So if we look at chlorine, chlorine has 17 electrons. Okay, and so let's fill up our energy levels. So we have chlorine, so 17Cl, is going to be 1s2, 2s2, 2p6, okay, that's 10, 3s2, that's 12, 3p, and then I'm going to go 5. 2, 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. So that's 17 electrons. This one's not so bad, but we can abbreviate this. And what we can say right here is we look at the inner shells, this filled inner shell right here, this 1s2, 2s2, 2p6. Let's take a look at a periodic table and see if there's a noble gas that has this configuration. So 1s2, 2s2, 2p6, so 10 electrons. 10 electrons, that's the neon electron configuration. So I can abbreviate this chlorine electron configuration by saying it has neons electrons plus these electrons. So let's write that out. So what I'll write instead is 17 chlorine, and then this inner shell right here is going to be neon 3s2, 3p5 right there. And that's a much faster way of writing it, because when I say square brackets neon, what I'm implying is all of these electrons. So when I say the filled inner shells can be abbreviated as they are the same as the nearest noble gas, what I mean by the nearest completed noble gas. What I mean by completed is I'm going to pull up the periodic table here, right? And the nearest completed noble gas to chlorine is neon. So the nearest, I look at the nearest completed noble gas. Well, the nearest completed noble gas is neon, so I square bracket neon, then 3s2, 3p5. When I look at tin, tin has 50 electrons, and that is going to be a very big electron configuration. So I'm going to pause the video now, and I'm actually going to fill this out for you, and you'll see how large the electron configuration is for tin. Okay, so as you can see here, tin has a very, very big electron configuration, and it's impractical to always write this out. So again, I look at tin's position on the periodic table, so I'm going to pull this up right here. Okay, and let's find tin. So tin is right here. So the nearest completed noble gas to tin is krypton, right? Krypton has its full electron configuration here. So I'm going to use the filled inner shells. I'm going to represent them as krypton. So krypton is 36 electrons. So all of this right here is represented by krypton. And so when I go to rewrite tin's shorthand or condensed electron configuration, I'm going to write tin, and then instead of writing all of these right here, I'm just going to write square bracket krypton, and then 5s2, 4d10, and 5p2. Thanks for watching.